This is the movie of my final project for the main 5000 math class. I'm going to be studying creep, which is an important phenomena in my field, which is the power plant design. And I'm going to be looking at power law creep, specifically the Bailey-Norton power law, where creep strain is equal to this formula and creep strain rate is equal to this formula. And you can see here I've plotted the strain curve, and the first part of the curve is primary creep. The second and fairly straight portion of the curve is secondary creep. The last part is tertiary creep to rupture. I'm going to be looking at secondary creep. So my assumptions are secondary creep. I will consider high temperature and high pressures, upwards of 1125 Fahrenheit, and pressures 4,000 to 5,000 psig. And I'll be looking at SA335 grade 91, which is a 9% chrome alloy, commonly used in large bore piping for coal-fired supercritical power plants. I'll be looking at 1D and starting with constant load and temperature. And we'll be looking at or establishing that the steady state creep strain rate is equal to constant B times the stress to the power n. This is the simplified power law formula where n is between 3 and 8. If you look at a log-log plot of steady state strain versus stress, you get a roughly straight line here for power law creep, where the slope is n equal to some value between 3 and 8 typically. And I'll also compare my results to a general creep equation. The change of strain versus time is this equation here, and if time allows, I'll explore large bore welded T's with stress intensification factors, and I'll use common material constants and parameters. And this will relate directly to Module 4 of the class, where we talked about methods of polynomial and trigonometric interpolation and approximation. I'm expecting that in some of these equations I may have to interpolate and or approximate values. And to date, I don't have any specific issues to comment on related to my progress to date. Thanks for watching.